I'll begin with a word of prayer. So, Dear Father, we thank you for this day again. I thank you for this class and this time we have to meet together and study your creation. Just pray that you'd help us use this time wisely just to draw together the end of the course, Lord. In my prayer, Lord Jesus. Amen. So we talked a little bit about analysis in here. And so I wanted to talk also about algebra. And what is algebra? Give you kind of the big picture of it. And I would say it's kind of a glib thing to say, but in a nutshell, more or less, algebra is concerned with equations and the study of the structure of equations, things like that. Whereas analysis is more concerned with, I would say, inequalities and the study of estimates, things like that. Now that's not really fair, and you can't really give a glib definition for either one of these fields because they're much bigger than both of the things I said, all right? It's just kind of and they're not mutually exclusive either, all right? Like there is algebra and analysis, there's analysis and algebra. For example, to prove the fundamental theorem of algebra, that every nth order polynomial has n roots, possibly repeated, possibly complex. Every known proof of that, as far as I know, at some point or another involves analysis. And the deeper the analysis that involves, the easier the proof gets. Like, there's a proof of the fundamental theorem of algebra that you can see in the complex analysis course here, which is pretty simple. I oftentimes put it on the final. It's easy enough for students to just do as a kind of a throwaway, easy final exam problem, believe it or not. On the other hand, if you prove the fundamental theorem of algebra using like calculus level algebra, the proof is considerably more involved, but you can see that proof in Math 422 if you ask for it. But the story of algebra basically goes back to antiquity, right? Linear equations are ubiquitous throughout applications, and quadratic equations of the form, say, ax squared plus bx plus c, well, these have to do with simple questions about really the geometry of squares and rectangles and so forth, right? If you've ever watched the video by Veritasium on completing the square, you can see it quite powerfully demonstrated there in terms of how, mathematicians of, say, the, 1200 to 1500, somewhere in there-ish, they used to really think of these in terms of like a geometric construction. So the different quadratics they thought of in connection to their geometric underlying, the underlying geometry of assembling a rectangle of a particular type. And you can still see some vestiges of that if you look in like college algebra books. They have problems where you're, like understanding multiplying a polynomial by groupings of boxes and things. You'll find these problems. But anyway, this, the quadratic equation has been known, the solution of it's been known since antiquity by different cultures, right? Like Babylonians had solutions, and so like this is very old, this solution to this, but relatively recently the cubic was solved, right? The cubic was solved, I think I have some details down here. Cardano in 1545 rather, and then Bombelli in 1572 pointed out that the cubic, this one right here, has 3 real solutions, yet the formula by Cardano necessarily involves complex numbers. So like complex numbers start to become a necessity of solving real equations even when you have real solutions, right? The complex numbers appeared in the general solution to the quadratic before, right? But you could kind of just say, oh, but that's just because those quadratics don't have real solutions. At this point, with the cubic equation, even when the answers are all real, the necessity of complex numbers appears. So, like, if you will, not looking, like having to work with complex numbers is almost forced upon you once you get to the cubic order, even if you're just interested in real solutions. And about the same time, Cardano, and then I think Tartaglia, I don't know if I have the whole history in here, but Tartaglia, a few others, basically they found the cubic and the quartic solutions in between about 1550-ish to, I forget what, I think it was all in this time period. And then, of course, you'd like to find a solution for the 5th order problem, right? The quintic. So, the quintic, I mean, I can solve some quintics, right? Like x to the 5th equals to 0. We can solve that. What's the solution? 0 repeated 5 times, right? There's just one solution, it's 0. Zero's all around. So we can sometimes obviously solve, but when is it not possible? And also, like, if I had like x to the 5th equal to 32, I could easily solve that as well. And you guys have started to see some of that this semester. Like, check this out. If I wanted to solve x to the 5th equals to 32, obviously I could use x equals to 2, right? But notice that if we look at e to the 2 pi I over 5, right? And we raise that to the 5th power, well, that gives us e to the 2 pi I, which, by the way, is cosine of 2 pi plus I sine 2 pi, right? Which is 1. And so you could graph it. Here's the 2 solution, and there's like one here, 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 and here up to the limits of my artistry, which is very limited. I think I need to make more down like here and here. We should have like if I did it right, this should be and I've not done it right, but if I did this right, these would all be equal length, okay guys? The point is, you've got 1, 2, 3, 4, 5 solutions, and so like this one would be 2, let's call this thing omega. 2 omega, 2 omega squared, 2 omega cubed, 2 omega to the 4th power, and this of course is just 1. These are the 5 solutions to x to the 5th equal to 32. See, once you know the imaginary exponential, you can easily write down solutions like that, right? Like the imaginary exponential is so useful, and you will see it again in like your future algebra course, right? But notice here what's going on. What can you say about the solutions to, I mean, you can kind of see it in this example, right? If I look at f of x equals to x to the 5th minus 32, notice that the roots, my horrible picture, but there's a symmetry going on here, right? If I have one of the roots, I can rotate into the other, right? If I know that there's a symmetry underlying here, I can, like, from one root I can rotate into the other roots. Yeah, see that? And so you might wonder, wait a minute, is it always possible to do that? Like, is it enough if I can just find one solution to a higher order polynomial equation? Is there some kind of generalized sense of rotation where I can rotate into the other roots? And the answer is sometimes. And this is more or less what Galois learned. Now, of course, Galois, what he was doing was built off, decades and decades of work by mathematicians like Lagrange, who essentially, the work of Lagrange and others in the late 18th century showed that the hope for finding a quintic equation through tricks similar to the ones that had been used to find the quartic and the cubic equations were not going to work. It became relatively evident that it wasn't going to work by about 1800. And then the hunt became, well, how can we prove it's not possible, right? Because, well, that's a tricky thing, because it's not that it's not possible for any fifth order polynomial to find a sort of quadratic formula. That is, a formula which gives you the solution to the quintic in terms of, an algebraic expression involving the coefficients of the polynomial, right? Like a quadratic formula. Evidently, it's not. I mean, there are fifth order ones like this one or like that one that you can find solutions in terms of, relatively simple operations on the coefficients. But it turns out that no, in general, it's not possible. And so Abel gave a proof that it wasn't possible in about, I think, 1820. And then in 1830 to 1832, somewhere in there, Galois gave what we now understand to be the Galois group construction, where he showed that you can take a polynomial, you can construct this thing we now call the Galois group, and if that Galois group is what's called solvable, if it's a solvable group, which has to do with quotients of subgroups being cyclic, it's got a technical definition that you could understand after like Math 421. If it's possible, if the Galois group is solvable, then it is true that the solution is obtainable by radicals, which is to say, like a quadratic formula. However, if the Galois group is not solvable, then it's not possible. And it turns out that you can give an example of a fifth order polynomial that has a Galois group which is called simple. which has a technical meaning, all right? A simple group is one which doesn't have any subgroups which are normal. In other words, a simple group is one which you can't form any interesting factor groups. A factor group, we did this thing with dividing by an equivalence relation. There's a notion like that. You can talk about two elements of the group being equivalent if they're in the same coset with respect to a subgroup. And if that subgroup is normal, you can define a group structure on the equivalence classes, as it turns out, called the factor group. And for a simple group, it's simply not possible to form any factor groups except the very boring one of the group mod all of itself, right? So simple groups are sort of in some sense atomic. They're not, you can't reduce them to more interesting factor groups. Anyway, so there is such a polynomial in the fifth order case, and because that fifth order polynomial has a simple Galois group, it proves that there does not exist a quadratic type formula for that. This was essentially proved by Galois, like I said, in 1832, who's an interesting character, right? Because this French dude, he died in a duel at age 20, and there's speculation if it was politics or a woman. I don't really know. There's a horrible, hilarious music. There's a song made about this where allegedly the name of his beloved was or one he would like to have pursued was Stephanie, but it's done in the style of the Old West. Which is kind of right by about maybe 40 years of history juxtaposed, but it was also in France. I don't know if you can find this song, it's really quite hilarious, and very wrong. But it also has a lot of actually decent history about Galois, ironically enough. But anyway, so that was the birth actually of what we now call group theory. Group theory is the lion's share of what we study in Math 421, right? Which is the first serious abstract algebra class. That's not entirely true. In terms of algebra here, we have, of course, math. You have linear algebra, like the first course, 221 here. I would say you might call it baby linear algebra. In that course, we only study basically the linear algebra over n-dimensional Euclidean space, right? So we study matrices, how to solve systems, basic computational linear algebra, and some bits about like diagonalization, some deeper things. But that's not really an algebra course per se. It's a computational mathematics course, really. Then in Math 321, we study the algebraic structure of vector spaces. That's probably your first real algebra course here. And of course, Math 321 is much more abstract than Math 221. Math 321 then leads you to Math 421 here, which is our first course in you might call it. So some people call it abstract algebra. Some people call it modern algebra. You'll find textbooks with either name. I think there's some textbook that's like abstract modern algebra. There's various naming systems here. So that's 421. Typically taught by Dr. Sprano. I taught it 3 years, and they're all on YouTube if you want to watch me. But then after that is Math 422, which I hope to teach next year. Math 422 is not so much about group theory anymore, but sometimes in Math 422 I'll spend a couple weeks on like elementary Galois theory. It turns out that Galois theory, by the way, it's a method that can be applied to things other than just the problem of polynomial equations. Like there is something called differential Galois theory, which asks a similar question about differential equations. Like, have you ever wondered if you can do an integral in terms of elementary functions? Like, when is it possible to integrate something and have it in terms of, exponential sines, cosines, your elementary functions? Maybe you heard in Calculus 2 that the integral of e to the x squared cannot be written in terms of like elementary functions, right? It necessarily has to be done by the power series technique, right? How do you prove such a thing? Well, answers to that kind of question are given by what's called differential Galois theory. Differential Galois theory studies extensions to differential fields which may or may not be solvable. And so there's an analog of Galois theory for differential equations called differential Galois theory, which is still a much more active, I'd say, well, it's a challenging research area. I don't know everything about it by any means. I just know that it's a thing. Anyway, so that was one direction which opened the door to group theory in about 1830. And I would say the better part of the period, like 1830 to 1900, a lot of that was spent sort of in part unraveling what's the meaning of Galois theory in part. And a lot of that had to do with the symmetry on the roots thing I was talking about, which all of those things were in terms of permutations of the roots. So permutation is a one-to-one bijection, right? In other words, it's a bijection. So you could look at the set of bijections on the roots of a polynomial. That's a permutation group. And so a lot of what we call group theory was just the study of permutations early on. But there's another direction that group theory developed from, which was the study of shapes and just the study of how you could, like how many different ways are there of seeing a symmetry between shapes in the plane, that kind of thing. Like what's the structure of what are called transformation groups? This was the other direction in which group theory was developed somewhat independently from the problem of solving the quintic equation or whatever, polynomial equations. And so there have been different motivating questions that have built together what we now call group theory and more generally abstract algebra. Okay, anyway, let me go on here. So so I just want to introduce to you some terminology here, and I may not actually test on any of this directly, but you will be tested on all of this directly in time, all right? Maybe not this course, but eventually. So I think it's worth just spending a few minutes trying to seed your intuition with this for future purposes. But what is a binary operation? A binary operation is simply something where you take two things and you make a single valued output. So it's basically a mapping from the Cartesian product of a set back to itself. So like we can take a pair of functions and compose them. We can take a pair of numbers and add them. We can take a pair of numbers and multiply them. We can add matrices. We can multiply matrices. These are all examples of single valued assignments from a pair. They're binary operations, all right? So at the heart of what an algebraic structure is, what a binary operation is. Like I was just saying, it's a function, which we now hopefully have a careful understanding of what function means, from A cross A to A. And we say a binary relation is closed on A, and we could denote the operation by star such that AB maps to A star B. Then A paired with star is a set with an operation star. Great. If we have two operations, maybe star and circle, then we have a set with two operations, right? And if a set has more than one or more operations in possibly several relations, we say that A is an algebraic system. So the real numbers are an algebraic system, right? We have two natural operations, addition, multiplication, and we have an order relation, right? We have less than is an order relation. And so these together are paired with plus, dot, and less than is an algebraic system with operations plus and multiplication. I should say addition and multiplication like a human. No one says plus and multiplication. What's wrong with me? Anyway, so now you might say, well, I already know what real numbers are, and I don't see how this really adds any value, Like you're just making up words. That's true. We are just making up words. But after a while, the value becomes apparent. And so that is kind of the deeper question of what we're doing, which is, what are we doing is abstracting things, right? We're trying to look at the mathematical examples that we've come to through various questions and pursuits, and we're trying to describe them in terms of axioms in such a way that we can prove things based on those axioms alone. And as such, we have proved things not just for the example at hand, but for all other possible examples which have the same structure. Let me talk about linear algebra for a second. So in linear algebra, Math 321, we prove a number of theorems about vector spaces. When you prove a theorem about a vector space, you've proved it not just for the one example of matrices or vectors or linear transformations, whatever those are. You've proved it for all possible vector spaces. There's an infinity of such things. Every time we prove a theorem about an abstract notion of mathematics, there's an incredible efficiency in argumentation in terms of we don't have to do it again. I find out something's a vector space. Oh, great, now I know it satisfies all of the theorems for vector spaces, right? There's an incredible efficiency in argumentation there. And not just that, it allows us to think about things at a different level. Rather than getting lost in the fact that it's a 12 by 12 matrix with 144 components, I just know it's a box of numbers that satisfies certain properties. I don't have to think about it in terms of the totality of its elements. I can think about it collectively as a unified object. Anyway, integers have, of course, addition and multiplication. So integers paired with addition and multiplication's algebraic system. This guy, hopefully you guys have learned this semester a little bit, like z mod n. Again, an algebraic system, because addition and multiplication modulo n are algebraic operations. Now, how about integers? How about even integers? Are those an algebraic with respect to addition? I think they are, right? Because if I add two even integers, I get an even integer. If I multiply two even integers, I get an even integer, right? So that would form an algebraic operation with respect to addition. What about odd integers? See, odd integers would not form. Well, it depends on the question, right? Odd integers with respect to multiplication, I think that would give us an algebraic system, right? Because the product of odd integers is odd. So I can assign the product of two odd integers to an odd integer again, right? What about addition? That I'm out of luck, right? If I add two odd integers, I get an even integer. I'm out of my starting point. But it is true that even integers paired with addition and multiplication do in fact form an algebraic system. Oh, look, that was my next example. What do you know? You can also talk about a set paired with an n-ary operation, which would be a function from the Cartesian product of A with A with A with A with A n-fold times, right? The n-fold product, Cartesian product of A to A. If n equals 1, we say it's a unary operation. So examples of unary operations would be like complex conjugation on the complex numbers. I take A plus IB, out pops A minus IB, right? That's complex conjugation. That's a unary operation. Can you guys think of any unary operations on the real numbers? I have a real number. I want to output a real number. What can I do to it? Yeah?
Would like exponents be considered unary, or is that technically?
Oh, sure. Yeah, we could square. That's a good idea. X squared. X maps to X squared. That would be a unary operation. Very good. I was thinking like minus, like just negation. Take a real number, negate it. That's a unary operation. There's infinitely many of these things you could think of. Let's see here. Of course, binary is n equals 2, and n equals 3 is called ternary. Oh, I guess I have it right here. I haven't read that yet. I guess I'm a creature of habit. There it is. Of course, if we look at the real numbers without 0, then reciprocation is a unary operation, right? Like 1 over x. There's in Calc 3, which some of you are possibly in, I think, and some of you are about to take maybe. In Rn, which is the set of n vectors, right, we can calculate the dot product. So the dot product takes in a pair of vectors and outputs a number. So this would be an example. Actually, this is not a binary operation. Why? Because the output is what? Is a real number, not a vector, right? So this would not be an example of a binary operation, in fact, although it's interesting. The dot product is interesting. Cross product, on the other hand, would be an example of an operation, because we take the cross product of two vectors and we get out another vector, right? So the cross product on R3 is a binary operation on R3. And an interesting question to ask is, like, are there cross products in other dimensions, you know? So you can define actually an n minus 1 array operation on, I think it was supposed to be Rn here. Oops. Oh, operation on R? Huh. What? I think maybe it's supposed to be Rn there. That seems like a typo. So like on R2, you can define a unary cross product like this. So here, actually, the question is like, what do you mean by generalized cross product, right? This is an interesting thing to think about. If you mean that you're trying to produce a new vector which is perpendicular to the given vectors, that would be one decent definition for what we mean by cross product, right? So if you give me AB, if I give you this vector, that's perpendicular to AB, right? If you take the dot product of this and that, you get 0. They're perpendicular. The angle between this vector and that vector is 90 degrees. So this is a sort of cross product in 2 dimensions. Cross product, quote unquote cross product, in R2 is essentially just rotation by 90 degrees. You got 2 choices, right? You could either rotate clockwise 90 or counterclockwise 90. Just like in R3, you could define a cross product which is by the left-hand rule or the right-hand rule. We use the right-hand rule because the left-hand rule, of course, is evil. But if you're in 4 dimensions, you could define a cross product using the sort of the mnemonic formula that we teach in Calc 3 sometimes, like I hat, j hat, k hat, and then you put the vectors down here. Well, you could do that for I hat, j hat, k hat, whatever the 4th vector would be. I don't know, t hat, w hat, whatever. And this would actually define a vector, a 4th vector, which was perpendicular to these 3. Anyway, this is not algebra proper. This is just me messing around. Let me move on. If you want to read more about that, ask me. My brother wrote a paper that talks about the generalization of the cross product, which is probably worth looking at if you're interested in that question. The other, of course, interesting generalization of the cross product is one of my favorite things, which is the wedge product. The wedge product is a way of combining vectors to make an object which is no longer a vector. It's a multi-vector, and that multi-vector has properties which are similar to the cross product, but it's also much more. The wedge product is very interesting. I spend a lot of time talking about the wedge product in advanced calculus if you come take it with me. I talk about the wedge product a little bit in Math 321 here because it is a way of formalizing the theory of determinants as well. But so here's some like general terminology we should all know, right? The commutative property means that A times B is B times A, right? The associative property means A times B times C makes sense, right? A times B times C is the same as A times B times C, right? Associative property. Unital means that there exists an identity element. So like anything times A is A again. Excuse me, the identity element times A is A again. And it works both ways. If the algebra has an identity, it's said to be unital. Invertibility. If you have an identity element on your set, your algebraic system A, its set is said to be a point is said to be invertible if there exists B such that A times B is E and B times A is E. In this case, we say B is the inverse of A with respect to the multiplication star here. And if every element of A is invertible, then we say that star is closed under inverses. All right. There's a lot of examples of this, right? Like non-zero real numbers works like this, right? Any non-zero real number has a multiplicative inverse. Non-zero complex numbers, multiplicative inverse. Non-zero rational number, multiplicative inverse, right? How about Zn? Well, Zn we get into trouble, right? Like Z6 everything doesn't have an inverse, for example, because like 2 times 3 is 0, mod 6, but neither 2 nor 3 are 0. Those are what are called zero divisors. So in terms of Z mod 6, only 1 and 5 have multiplicative inverses. If we talk about Z mod a prime, it turns out every non-zero thing in ZP has a multiplicative inverse because the GCD, the greatest common divisor of a prime in any number which is less than that prime, right, is 1, right? Like 5 is relatively prime to 1, 2, 3, and 4. That means that 1, 2, 3, and 4 all have multiplicative inverses mod 5 because of the Bezout theorem that we talked about. So one of the things you have to get used to in Math 421 is the concept of a group being an abstraction of the notion of algebraic operation. There are different kinds of algebraic operations. For different, even for one set, there can be more than one notion of an operation, right? But generally speaking, if we call an operation addition, it's kind of assumed that it's an abelian operation. In other words, that A plus B is equal to B plus A. Multiplication doesn't have that assumption, obviously. And I suppose there's nothing stopping you from using plus for a non-abelian operation, but honestly, it's kind of a jerk move. Like, we should reserve the addition notation for abelian groups, for groups where you have commutativity. But here's the typical notation. We use this exponential notation for multiplication, and we use this negation notation for the additive inverse. So like additive inverse, multiplicative inverse. These are related, but quite different, right? The identity is 1 for the multiplication, the identity is 0 for addition. A lot of times we also use like an E for the identity in group theory. In the context of, you can talk about functions forming a group under composition. In that context, the identity is the identity function, actually, on a set. So what's a non-associative operation? A nice example is the cross product. So like if you calculate this cross product, you get 0. And if I was to calculate the cross product in the other order, I get minus k. So obviously 0 is not equal to minus k, so this and that are different. So what I'm doing is I'm first taking the cross product of I plus j with j here. Down here, I'm first taking the cross product with j with k, right? So if this was an associative operation, I should get the same thing, but I don't. The cross product is not associative. Do you guys know? Another good example of a non-associative operation is like subtraction, right? You can't, it matters which one you do first. But the cross product is part of a larger story. While the cross product is not associative, it does satisfy what's called the Jacobi identity. And so like, if you said like v comma w was v cross w, so like that would define what's called the Lie bracket of two vectors. A Lie bracket is a way of combining two elements to make a new one, and the Lie bracket has to satisfy this particular identity. This is called the Jacobi identity. It's a weakened associativity condition, and a good example of a Lie bracket is the commutator bracket, which is simply defined by AB minus BA. So the study, you can study Lie algebras. Like I took a whole course on Lie algebras, just studying what's the theory, the structure of Lie algebras. Lie algebras, in short, it's a vector space paired with a Lie bracket. There's also something called a Lie group. A Lie group is, all it is a group in the sense of group theory, whatever that means. Well, it means four things. A group is simply a set with a binary operation, which is associative, closed under inverses. I think that's it. So, for something to be a group, it has to have a binary operation. That binary operation has to be associative. There has to exist an identity element, and every element has to have an inverse. This is what we mean by group. A Lie group is a group which is also what's called a manifold. A manifold is a concept of space which allows for local calculus. So a Lie group is simply a group which also allows for calculus. It turns out to every Lie group there corresponds a Lie algebra. Like there is, if you look at the tangent space to a Lie group at the identity, it is a Lie algebra. There's natural identification there. So, and it turns out that there's a whole correspondence between the theory of Lie algebras and the theory of Lie groups. There's what's called a functor. A functor is something in mathematics where you go from one world to another, and not just that, you have a way of transferring sets to new sets, and also mappings to new mappings. A functor, it transfers both sets and mappings, and it also will naturally map together compositions in a certain order. There's two different kinds of functors. There's contravariant, there's covariant functors, and there are functors that go between different worlds of mathematics. Like we study as we go on, we have different categories of mathematics. There's like the category of set theory. The category of set theory just has sets and functions. That's kind of it. The isomorphisms in the category of set theory are just bijections between sets. There's a category of there's a kind of a linear algebra category where you have vector spaces and linear transformations, and there the isomorphisms are literally like isomorphisms in the sense of linear algebra. There's a category of topological spaces. There the sets are topological spaces, and the mappings would be continuous mappings of the quote-unquote isomorphism there is what's called a homeomorphism. A homeomorphism is a continuous map with continuous inverse. Two sets are said to be topologically the same if there exists a homeomorphism between them, which is to say that they're homeomorphic. There's a category of differential. There's a category of smooth manifolds where The sets are manifolds, and the two sets would be equivalent if there exists what's called a diffeomorphism. A diffeomorphism is a one-to-one correspondence, which is also smooth with smooth inverse. So there's all these different categories of mathematics, and there are theorems which are true for all the categories. The study of theorems which transcend a particular category is what's known as category theory. We do not have a course in category theory. I do not know category theory that well. I have had a student who was obsessed with category theory before. There are many resources online. If you're obsessed with it, you can learn yourself. And you can become incomprehensible to me very quickly if you do so desire. My advisor spent like 2 years researching category theory, and he was happy that he proved a theorem. It's just, I don't know. It's so abstract. It's like perhaps the most abstract mathematics. Maybe, I don't know. But anyway, there are functors between categories are very precious. And for example, there's the exponential. Actually, the matrix exponential is kind of such a thing. The matrix exponential, if you have a Lie algebra, which is a matrix Lie algebra, you can take the matrix exponential of that, and that will take you to a matrix Lie group. And it turns out that there are theorems that are known for Lie groups, all right? And there's a transference of those theorems over to Lie algebras. Like there was a bunch of people who got PhD topics. Basically, their whole PhD work more or less was translating a theorem that was known for Lie groups into a corresponding theorem that was known for Lie algebras, right? Just because you have a feeling that it's over there doesn't mean it's there. You actually have to prove it exists and so forth. But where I went to school, NC State, there was a sort of a cottage industry of that for a time where people were taking known famous theorems of Lie groups and finding corresponding theorems of Lie algebras. Lie algebras and Lie groups are important to many applications because essentially modern physics at the moment is built over the representation theory of matrix Lie groups. So a Cayley table is something you'll study in Math 421. It is basically a tabular representation of all possible products in an algebraic structure. So like here's the Cayley table for Z3, addition, multiplication, right? Sometimes people don't bother writing this column or this row because 0 times anything is 0. So do you really need to write those? I don't know. On the other hand, if you just focus your attention on 1 and 2, 1 times 1 is 1, 2 times 2 is 1, right? 1 times 2 is 2, 2 times 1 is, so that actually is a group if you just focus on the non-zero elements in Z3. I have a bunch of Cayley tables at the end of the chapter on modular arithmetic, if you remember. Right? I write out multiplication tables for like Z mod 5 and some other things there if you go back, right? Those are all Cayley tables. In as much as it's I guess I should be careful. I think a Cayley table is specifically for a group, but you could talk about multiplication tables for something that wasn't a group. And in fact, if you're very ambitious, you can try to understand what does the Cayley table have to look like in order for it to be a group. There's some things that are relative. I'll leave that for Math 421. It's a complicated story a little bit, but so there's some theorems which we could prove. For example, if we have a algebraic structure, then it has at most one identity element. All right, you can prove that the identity element has to be unique through the paragraph that's given there. If it's an associative operation, then each invertible element has a unique inverse. So you can prove that the left inverse and the right inverse are equal. But not always the case. Let's see here. A lot of times we also like to use juxtaposition for an operation, and this is oftentimes the case, right? This is most of what we do, right? You don't, when we talk about x squared, let's forget about x for a second. You talk about a squared. Do you write axa? We don't do that anymore, right? We just write a dot a, or perhaps a parentheses a, right? Or just aa. That juxtaposition is a notation for multiplication, right? When in your youth you wrote out a cross symbol for multiplication, right? If you write that now, I kill you. Don't do that. It's almost as bad as mixed fraction notation at this point. Don't write 1 plus a half Well, right, 1 plus half, that's great. 1 plus a half is fine, right? This is okay. This is okay. This is not okay. This is bad notation, right? Check it out. 1 and 1/2, 2 and 1/2, right? If I multiply this by 2, cancel the halves, I get 1 equals to 2, right? It's very bad notation. We should not teach this notation. Like, putting a little plus here makes all the difference in the world. You know? That little plus is important. But anyway, my ranting about arithmetic aside, let's go on. So, so again, here's the formal definition of group. A group is a set with a binary operation, which is, like I said, identity element, associative, and it's closed under inverses. This is a group. An abelian group is one for which A times B is equal to B times A. That is in honor of Abel, who's the one who proved that there was no solution to the quintic. But he didn't take the, so Galois took an extra step, right? He not only proved it was impossible, he proved when it was possible by talking about the Galois group. If you have any set, non-empty set, you look at all of the bijections on this set, that forms a group called the permutation group. Right? Permutation groups are important. The symmetric group is one of your first examples and most important examples of a group. It's simply the set of permutations on 1, 2, 3, n. I'm on the cusp of teaching that in here because we actually need permutations in other math classes besides Math 421. Properly speaking, I would really like to have the full theory of permutations for Math 321. I'm like on the bubble of teaching this in Math 321 just to make sure that we have like the full theory we need. But then again, there's a lot of things to teach, so I usually let it wait till Math 421. There's a special notation for the permutation group called cycle notation, which makes the computations way, way easier once you know the cycle notation. But the cycle notation there's a little bit of a learning curve there. So, that's the problem. That's why I don't always go full bore permutation group early on. Sachs-Schuh's theorem. If you have a group, the inverse of the multiple is the multiple of the inverses, but in opposite order, right? Sachs-Schuh's because first you put on your socks, then you put on your shoes. But when you undo it, most of us have to take our shoes off first, right? Somebody in here is going to be wearing sandals with no socks or something. I'll kill you. No? Okay, good. Although I guess sandals with socks is worse, isn't it? I don't know. Oops. Wait a minute. Oh my goodness. Well, I don't need to say all these things. You can read. This is just a quick overview of like group theory. The inverse of the inverse is the element again. We have cancellation laws in groups. This is basically week 1 in Math 421, okay? Well, Dr. Sprano does teach some, he might not get to the definition of group right away. Like he's got other more basic things. He talks about posets and things that are sort of underlying before group theory stuff that he does. But once he defines a group, these will quickly follow everything I'm saying here. This is one of the struggles, is like in a multiplicative group, a to the n means n-fold multiplication of the element by itself. A to the minus n means n-fold multiplication of the inverse element by itself. Actually, we've talked about this in here before. But on the other hand, n times a is actually n-fold addition, or minus n times a is n-fold subtraction, n-fold additions of the additive inverse. So there's, these are notations that are both defined carefully in terms of a recursive rule, right? And you can talk about subgroups. A subgroup of a group is a subset, which is also a group with respect to the operations. There's a subgroup test. There's things called cyclic groups, generators, all these things. We've talked a little bit in here. I've asked you some questions about, wait a minute, have I? I don't know if I have, but we could talk about, I think we had a homework problem where we contrasted the additive order of an element, right, versus like the number of elements in something, so we did that. Ultimately, what you're really interested in, the deeper question of group theory, is if you're given two different groups, right, are they in fact the same group with different notation, right? If that's the case, the groups are said to be isomorphic, right? Now, sort of the more basic question is, you've got two sets. When are they really the same? When are they the same number of elements? That's kind of a gross version of that question, right? Because if they're the same group, the first thing that they should have is the same number of elements. So to prove two groups are isomorphic, first of all, you need a bijection between them. But that's not enough, right? Because a group is not just a set of elements, it's a set of elements paired with a multiplication. So to have two groups being the same, you need that there's an order preserving map. You see, like phi of x times y is equal to, like this right here, phi of x times y is phi of x composed with phi of y. So here I'm using star for the multiplication, the operation in A, and I'm using circle or composition, if you like, for the operation in B. And so there has to be like a preservation of operations. If that's the case, such a function is called a homomorphism. If that homomorphism is also a bijection, then it's said to be an isomorphism. All right, of groups in this case. There's also isomorphisms of linear algebra. There's an isomorphism of smooth manifolds, but then it's called a diffeomorphism. There's an isomorphism of topological spaces, but then it's called a homeomorphism. But all of these, the idea is a bijection which preserves the structure which is involved. This is what an isomorphism is. Anyway, let me go on here. Just end with this, basically. So overall, in Math 421, which is your introduction to, like, abstract algebra, you'll talk about groups for the lion's share of the semester, and then towards the end, you'll also talk about a ring. Some people say ring by spring. I say rings by October when I teach Math 421, but it works. Quiet. So a ring is a set paired with two operations. It's got addition and multiplication, and they have to work together nicely. For one thing, the addition has to be abelian, and the multiplication has to be associative. And they also have to get intertwangled in the right way. They have to have these distribution rules, like multiplication of the sum is the sum of the multiples, and the multiple of a sum is the, well, anyway, both of these distribution rules. And there are lots of rings, lots and lots of rings, complex numbers, real numbers, rational numbers, integers. These are all rings with respect to the natural addition and multiplication. Z mod n, also a ring, all right? So once you've defined a ring, you also define what's called an integral domain. An integral domain is a commutative ring with unity that has no zero divisors. So, for example, Z mod 6 is not an integral domain because 2 and 3 are zero divisors, all right? On the other hand, Z mod 5 is an integral domain because in Z mod 5, 1, 2, 3, 4 are not zero divisors, and 0 is not a zero divisor by definition here, okay? So Z mod 5 would be an integral domain, whereas Z mod 6 would not. All of your favorite reals, rationals, complexes, integers, these are all integral domains, and Z mod a prime is also an integral domain. In fact, there's a theorem that Z mod any prime is a field. What's a field? A field is an integral domain such that multiplication restricted to the field without zero is closed under inverses. In other words, a field is a commutative ring with unity such that the set of non-zero field elements is an abelian group with respect to multiplication. So a field is kind of sort of a group both with respect to multiplication and addition. That's a lie. It's not quite that, right? Because again, 0 doesn't have a multiplicative inverse. Another way of saying it is a field is a set where every element that's not 0 has a multiplicative inverse. And also there's an addition and a multiplication which behave like normal. That's sort of a lowbrow definition of what a field is. But of course, these are all fields, and Z mod prime is a field. The study of fields is also known as field theory in mathematics, but this should not be confused with field theory in physics, which means something radically different. All right. So we study, the abstract structure of fields is more typically studied in Math 422 here, which as a math major, I think you have an option either of taking Math 422 or you can take the, goodness gracious, I think it's Math 411, like one of the more difficult statistics courses. Of course, it depends on what kind of math major you are and such, but anyway, just wanted to give you kind of a lay of the land. This is what's forward in terms of algebra. In terms of coursework here, of course, we have the calculus sequence, which is more or less in the realm of algebra, analysis, really. But there's some algebra in the calculus sequence, right? A little bit, but not too much. And then we have complex analysis, which is an analysis class, obviously. Although it's not as sold out to rigorous analysis, right? It's still sort of a computational math class in a large part. We have a differential equations class. That is full bore computational math class. We don't prove anything in there hardly. There are deeper questions of analysis in differential equations which we don't answer there because it's a service course for engineers. But largely speaking, I think it's an interesting course. It's an easy course, relatively speaking, to other things that are 300 level. We have, of course, Math 307, which is elementary number theory. That is a good preparation for Math 421. You'll be much more used to concepts of primes and a lot of Math 421. Some of the examples are shared by Math 307. So it is the opinion of Dr. Sprano and myself that if you take 307 before you take Math 421, it's helpful. You don't need to though. It's certainly possible not to. But Math 307 is interesting. In terms of applications, 307 has tremendous applications in terms of cryptography and things like that, right? Like I think Dr. Schmidt will actually talk about cryptography, the RSA encryption, at least a little bit in Math 307. Let's see, what else do we have? Math 352 is numerical methods. That's Dr. Wang's course typically. That's an incredibly useful course. Even if it's not on your DCP, it would be wise to take it, especially if you're not sure you're going to be a teacher. If you think you might be doing mathematics in like an industrial setting or something, that course is invaluable. Because it's more about, at least a little bit about how we use computers to do interesting calculations, things like that. It's not just that though, it's not a computer course per se. What else is there? So many things. We have a lot of options in the math major here. Of course, you have three different paths, right? They have a few different versions of the math major you can choose. But I would encourage you to don't just take what you're required, try to take more, And if you're thinking about going to grad school, it's especially important to demonstrate that you have a passion for mathematics, and one way to do that is to take things that you're not required to take, right? If I'm a graduate school and I see a student who's taken what they've required and nothing else, I'm like, well, that's good, but it'd be better if I'd seen that they tried to do more than that was required of them, I mean, I think we'd all like to have employees that do more than is required of them, right? Especially if they're not acting against you, if they're acting for you, So anyway, any questions? What's on the final? I will we have solutions to everything posted, so you can look at them, obviously. And in terms of definitions that I expect you to know for the final, everything I've said today, pretty much without exception, is irrelevant. All right, so don't worry about that. I wanted to give you guys some picture of what's past this course a little bit. There's so much more, by the way. Math is so much bigger than what I've said today. So in terms of advanced courses that we don't have on the books, topology is a good example of that. Dr. Sprano has taught topology a handful of times in the last decade, and that's not a required course, but it's a course that we run when there's interest. I've taught a truckload of different independent studies on different things over the years, according to the interest of students. I try to keep doing that. Okay, so getting back to your final, fine. I should make an announcement which has an attempted. I will try for a comprehensive list of the definitions I expect you to know, but I would say, as a general point of order, it should be pretty much everything that has ever appeared in a mission or a quiz, So union, intersection, you know, the arbitrary unions, the arbitrary intersections, set difference, silly things like the empty set, right? I might forget to put that on this list. My apologies if I do. So, you know, what's the relation? Obviously, surjective, injective, bijective, cardinality. And as you go back, there's some things you're probably rusty on that you need to review the proofs of. Like, how can we best prove that square root of 2 is not a rational number, right? We did that. It's still very much possible on your final. So you probably need to review that at this point, right? And if you go back towards the end of that, we found an easier proof than the one we first found, right? There's a proof that uses a certain theorem on divisibility that was better. So I will try to hunt that down and put that in the announcement for you guys. There was also an unfortunate typo, I think, in the like the take-home part of test 1, was it? Anyway, now I'm getting into the weeds. So I would encourage you, like, go back, review the solutions to the missions that I've written for you guys, and you know, review the quizzes that we've had, review the tests, see what you got wrong. Almost like most of you are still like very, very wrong on the way you're proving surjectivity. Like, you have lots of company in here if you're doing it wrong, like a lot. Trying to prove surjective, we've got a function like f that goes from, let's say, a to b. How does the proof begin? The proof begins with let y be an element of b, right? I mean, perhaps you state the preconditions, like suppose the composite is whatever, et cetera, et cetera. Those kinds of things, fine. But shortly thereafter, there should be a clear statement of I'm picking an arbitrary element in the codomain, and I go from there. When you start dabbling with data before you've done that, I'm going to take off a ton of credit because you have not listened to me. And it's important that the surjective proof begins with a clear, you know, announcement that we're looking at an arbitrary element of the codomain. Let me load up quiz 12 solution here. Like, suppose G composed with F is surjective. Fine, fair enough. That came before my Y is an element of A, right? But shortly thereafter, let Y be an element of A. Why? Because I'm trying to show that G, which goes from B to A, is surjective, right? So I have to pick an arbitrary element in the codomain. Then I can, you know, as G composed with F is surjective, there exists X in A for which G composed with F of X is equal to Y. But that means that G of F of X is equal to Y, which means that there's F of X in B, right? So there exists F of X in B for which F of X maps to Y, which is to say that under G, which is to say, of course, that G is onto, right? So, but it's important that, like, so what you guys are typically doing is you're thinking through it, which is great, but it's not the end, you know? So we can't start with this, all right? We need to start with this, is all I'm asking, yeah? So this continues to be an issue on the quiz from what I saw. The other thing is you guys have studied, which is wonderful, but I did not say here that F composed with G is the identity. I changed the problem. See, it doesn't need to, you don't need to be given that F composed with G is the identity to prove problem 1 here, right? It's more general than that. So it is enough to know that the composite is injective to prove that the inside function's injective. It is enough actually to know that the composite's surjective to prove the outside function is surjective. You don't actually need that the composites are the identity functions. Those are special, you know, it's true, but let's see here. This here, you guys are like, I don't know what you're doing. Like, I don't know what's going on here. Everybody's wrong about this one, almost without exception. To prove it defines a function, a couple of examples will not do. You must give me proof that it works for arbitrary representatives. So if I have, you know, x30 is equal to y30, that is to say that the difference of x and y is a multiple of 30. which when I look at 2x plus y minus 2x plus 3, I get, of course, twice the difference of y and x, which is twice 30, which is, by the way, 5 times 12, which just shows you it's a multiple of 5, right? As such,